So this is sort of like used in conjunction with your rational root theorem that we talked about last week where we did plus or minus p over q. Okay. And remember, in the rational root theorem, the idea is let's make this list of possible rational zeros and we'll narrow down the list of numbers to check with synthetic division. We're looking for that zero, that happy face. But we're going to say, like, if a rational zero exists, it has to be on this list, plus or minus p over q. So don't check anything that's not on the list because it's not going to work. You're wasting your time, right? Descartes' rule of signs can be used in conjunction with that to take that list from rational root theorem and make it even smaller. So what you might find with Descartes' rule of signs is there are no positive real zeros. If there are no positive real zeros, don't check any of the positive numbers on the list. Okay? Or you might find out there's no possibility for negative real zeros. If there's no possibility for a negative real zero, don't check a negative number. You're wasting your time. Okay? So it's just an option that we know by pattern of polynomial, by the signs of the terms, that we can determine how many possible positive zeros we might have or how many possible negative zeros we might have. Now, it does have that tricky word possible in it again. So it means it could have this number of positive real zeros or it could not, right? So then that sometimes Descartes' rule of signs is super helpful and sometimes Descartes' rule of signs is like, didn't really help me at all. Now I still got to check the whole list or check at random, okay? Here's how the rule works for the positive zeros. You want to figure out how many possible positive real zeros there are for a particular polynomial. Should I even check any of the positive numbers in the list I made from plus or minus p over q? You're going to count the sign changes in f of x. So f of x is the original function. Like whatever problem I give you, count how many times the sign changes from term to term. So like, is the first term positive and the second term is negative, that's a sign change. But if you have all positive terms, there are no sign changes, so there's no possible positive real zeros. There is a small caveat to both of these for positive and negative. So you count up the sign changes that exist, and your number of possible positive real zeros is going to be equal to this number. And when I say equal to this number, I mean to the number of sign changes. Or it's less than that number by an even value. And this is where sometimes Descartes doesn't always give you really valuable information. It depends on what the sign changes look like. So just kind of like put your pencils down for just a moment and just kind of like hear me out on this so you kind of understand what that second bullet point is saying. Suppose I'm looking at my original function f of x and I count that there are 0 sign changes. They were all positive terms or they were all negative terms. Then there are 0 possible positive real zeros. And that would mean in my list of plus or minus p over q, don't check any positive numbers because they don't work. If I count my number of sign changes in my original function f of x, and there's one sign change, like one time a term changed signs, and then after that it was always the same, okay, then there's one possible positive real zero, which means it has to exist. There is a positive real zero out there. Okay, so a zero that shows up to the right of x equals 0. I would consider this equal to that number 1 or less than that by an even number, but 1 minus an even number 2 is a negative number of real zeros, and that doesn't make sense. You either have 0 or you have more than 0. Okay. So 1 could be an answer, and I would know that 1 existed. Now, what if I count the number of sign changes and there were 2 sign changes? Okay. So what I know from that in Descartes' rule of signs is maybe there are 2 positive real zeros out there, so they show up on the right side of my graph, x-intercepts, 2 of them, or less than that by an even number, 2 minus 2 is 0. Or maybe there's no positive real zeros, like no zeros show up over here. So you would, if you counted 2 sign changes, you would say 2 or 0. If you count 3 sign changes, you'll say 3 or 1. You wouldn't go any lower because that would be negative, and that wouldn't make sense. If you count 4 sign changes, it would be 4, 2, or 0. You just keep subtracting 2 until you get to 0 or 1. Okay. If you count 5 sign changes, it's 5, 3, or 1. So when you get to those where you have lots of sign changes, then Descartes maybe isn't as telling because you're like, well, I don't know, maybe they're all positive. Maybe none of them are positive, right? So I don't have as much information when I have more sign changes. Okay, the rule for negative is very similar to this, okay? But there's one big difference for negatives. When you want to count the possible negative zeros, so these would be zeros that, like, you know, you're looking at your graph, you got your y-axis. The positive ones would be on the right side of the y-axis. The negative zeros are going to be on the left side of the axis in the negatives. You have to count the sign changes in f of negative x. So you're going to see, I'm going to do f of negative x for each problem when I'm doing Descartes' rule of signs. I have to go to my polynomial, and every term that has an x in it, I have to replace it with a negative x. And then I have to simplify each term, like does that term keep its original sign or does it change its sign? Okay, so that I can go through and count the sign changes. So you count the sign changes, not in the original, because we already did that for positive, but in f of negative x. And then the rest of the rule is the same. After you figure out what f of negative x and you count the sign changes, it's equal to that number or it's less than that by an even value. So remember, if you're counting something greater than 0 or 1, you're going to have ors in your answer. You're going to have multiple possibilities. AC, you want to put that right here? Okay, so we'll do some examples and put this to work on counting the sign changes. Yes, Maddie?
When you say less than that by an even value, do you mean that the number of zeros you'll get would be even, or do you mean the number away from that number?
The number away from that number. So like basically whatever number you count for sign changes, you just subtract 2 as many times as you can, because that would be subtracting even numbers, 2, 4, 6, 8, until you get to 1 or 0. Okay, so make sure you put this one in your notes so that you have an example. F of x equals 3x to the 4th minus 7x cubed plus x squared minus 13x plus 8. And if I read the directions here, this is going to be similar to what they're going to ask you to do in your homework. Determine the possible numbers of positive reals, negative reals, and then also imaginary, which I didn't mention, but I'll kind of show you where that comes from. Imaginary zeros for this polynomial. Okay, so this is f of x, the original, right? And I'm going to get to counting its sign changes here in a minute. But I'm also going to say, like, in order to use Descartes' rule of signs, I also need f of negative x. So I'm going to go through this whole polynomial, and everywhere I see an x, I'm going to put a negative x. Now, this is my first go-round, so I'm going to do it for all of them. At some point, I kind of noticed something where maybe I don't have to write this step out every time. But everywhere I saw an x, I protected it with parentheses and I put a negative x in its spot. Okay, now I got to go through this whole polynomial f of negative x, and I got to simplify each term. So if you took a negative x and multiplied it by itself 4 times, what would happen to it? It would be positive. So this will really be a positive x to the fourth multiplied by the positive 3 in front. Do you agree that that term did not change signs? It was 3x to the fourth in the beginning, and it's still 3x to the fourth now? Okay. Okay, what would happen if you took negative x and you cubed it? Multiplied it by itself 3 times. It would stay negative, right? A negative times a negative times a negative is a negative x cubed. So then this would be a negative x cubed times a negative 7, which would turn it into a positive. So notice what happened here. It used to be negative 7x cubed, but now it's a positive 7x cubed. Okay, go to the next one. What happens when you do negative x quantity squared? It's just x squared. It's just a positive. So this one is not going to change signs, right? It's going to be plus x squared. Negative 13 times negative x? Plus 13x. Look at that. It used to be negative 13x. Now it's a positive 13x. And then the last one doesn't have an x in it, so of course it's not changing signs, right? It's just going to be plus 8. Could you make up a rule for like when your term changes signs? Will you tell your group? What would be a rule? When should you change a term sign?
When there's an odd.
Okay, I'm hopeful that you and your groups had a conversation about odd and even exponents, right? If it has an even exponent, does your term change signs? No, it stays the same. If it has an odd exponent, does your term change signs? Yes, it changes because then that value will be negative. Okay, so we'll use that shortcut and we won't write this middle line on the next one. All right, now let's go in and count our sign changes. Okay, let's do f of x. Okay. So it was a positive in the beginning, and then it goes negative. So there's one sign change. 2 sign change. 3 sign change, and 4 sign change. You see that? Every term it alternated signs, so the sign changed 4 times from term to term. So for the positives, there were 4 sign changes, but we know it could be equal to that number or less than that number by an even value. So it could be 4, 2, or 0. Now let's do the negatives. Sign changes. None. So no matter what, I have 0, negative, zeros. Okay. So I could have 4 positive and 0 negatives. I could have 2 positives and 0 negatives. I could have 0 positives and 0 negatives. If there were like 2 or 0, I would have to like say it could be 4 or 2, 4 or 0. Like those would be matches that I could make. But now I can fill in this. If I had 4 positive and 0 negative, how many imaginaries would I have? What was the degree of that polynomial? 4. How many zeros should you have for a fourth degree? 4. So if I have all 4 of them, then I would have 0 imaginary. If I have 2 positives, 0 negatives, then I must have 2 imaginary solutions. And if I have 0 positives, 0 negatives, then I have 4 imaginary solutions. Now we're going to do the solving part tomorrow where we actually utilize this, but this is a great example of, so Descartes' rule of science told me that there were 0 and negative values. So when I make that list plus or minus P over Q, I'm not going to check any of my negative ones because they will not work, without a doubt.
So for all of the imaginary solutions, every single, see how there's 2 and 0 and 0 and 0, all of those have to be equal to the degree.
Yes. So if you wanted to, you could think about what's the total zeros. It equals the degree. So it always adds up to 4. Okay, let's do one more. Okay, we'll run through this one faster since we've seen it before. Okay. Determine possible number of positive, negative, real zeros, and also imaginary zeros for this polynomial. Now, you might be worried just kind of glancing at this polynomial because what? It's missing x squared. So the coefficient to the x squared is 0. 0 is not classified as positive or negative number. So it just does not affect your sign change. You just ignore that term. So if you're ever missing a term, you can just still count sign changes like normal. Because 0 wouldn't be a sign change. It is neither. Okay, let's do f of negative x. Will the first term change signs? Yeah, because it's x cubed. It's got an odd exponent, so it's going to be negative x cubed. Will the second term change signs? Yeah, it'll be negative 9x, and then this one will be minus 25. It doesn't have an x, so it won't change signs. Let's see. Count your sign changes in f of x. Looks like 1. So for positives, I have to have 1. Count my sign changes for f of negative x. None again, right? So there are 0.
Why doesn't the negative x cubed be a sign change?
I'm not counting the sign changes from here to here. This is for positives. I count the sign changes in f of x, the original function. This is positive, this is positive. That is not a sign change. This is positive, this is negative, that is a sign change. And then when I want to do the negatives, I'm counting the sign changes down here. But I'm not going from here to here. So I have to have 1 positive real 0. I have 0 negatives, which means there must be what? 2 imaginary. So again, we'll use this tomorrow. I would definitely do synthetic guess and check until I find the 1 positive real 0 that works. And then after that, I will write out the quadratic and do quadratic formula because it's imaginary. I'm not going to be able to factor it. Okay, other questions that you may have? Yes, Kenzie? Yes, Alex?
On the positive, negative, imaginary, would we put 0 positive, 0 negative for imaginary?
No, because for a positive, it could be equal to that number, sign changes 1,
Okay.
or less than that by an even number, but 1 minus 2 is negative 1, and you wouldn't say you would have negative 1 positive real zeros. You just would have 0 of them. Okay, so you'll have some practice where you're going to do that with Descartes' rule of signs. Okay, so you'll need to write out f of x and f of negative x. I'm going to do just really quickly an example of the complex conjugates theorem. Okay, so that we got this down. This would have went really nicely with what we did last Friday with writing polynomials. And it'll flow really good. It just says like the imaginary zeros, just like the irrational zeros, they come in pairs. If a plus bi is a 0, then a minus bi is also a 0. It's conjugate. And that would be a great thing to like think about too, Alex, when you said, would I make it 0, 0, 3? No. Imaginary zeros won't come in odd numbers because they have to have a partner. They have to have their conjugate with them. So they always come in pairs. All right, write the polynomial with the following zeros. If my 0 is at 1, my factor looks like x minus 1. If 2i is a 0, that would look like x minus 2i. But then I know negative 2i is also a 0. So I would also have x plus 2i. Those are easy to multiply, right? If you want to like FOIL them out, okay, you could. X times x is x squared. I'm going to do my outside and insides together. Plus 2ix minus 2ix. Canceled out. Okay. And so the only other thing I really need to gather from that is negative 2i times positive 2i. That's negative 4i squared. And do you remember from chapter 3 what is true about I squared? It is negative 1. So this is really x squared plus 4 times x minus 1. So that will be x cubed minus x squared plus 4x minus 4 in the end. Mm-hmm.
Why would it be a negative 1 in the parentheses?
If the 0 is 1, then you're saying x equals 1. So if you were moving that back over to the other side, the factor must have been an x minus 1. Whatever your k is for your 0, remember, it always goes back as x minus k in the factor. You just got to move it to the other side when you solve. All right, and then I'll do just one more where we have like this would be like what we did in our warm-up. What if your imaginary 0 I give you is negative 4 plus I? Then the other one is negative 4 minus I. Write out my 3 zeros as factors. So that's f of x equals, this will be x plus 3. This will be x minus negative 4 plus I. And x minus negative 4 minus I. Distribute that negative. That's x plus 4 minus I and x plus 4 plus I. If you don't ever try to write down the factors and distribute the negative, then it looks really hard. Okay, but once you do it a few times, you kind of get used to what you're doing. It isn't so bad. Does anybody have any questions about why my signs are what they are? Most common issues I see is like, so someone will distribute the negative, and then this one is minus and this one is plus. And that would never happen. Like these first two will always be the same, right? So that I can group them. That's going to be an x plus 4 squared. When I FOIL it out, I'll have a plus I times x plus 4 and a minus I times x plus 4, so won't those cancel? And then I'll have a minus I squared. Negative I times positive I. It's negative I squared, which is really negative 1, which is really plus 1. So this is x squared plus 8x plus 16 plus 1. So x squared plus 8x plus 17. And then I had, I think, an x plus 3 that I still have to multiply by. Okay, so you get an extra chance. Yep, that's fine. You get an extra chance to practice that whole like multiplying things out. But this is really nice if you recognize that you can group those two together and then they're basically conjugates after that. They're always going to cancel out their outside and inside terms. Okay. So on your gold sheet, remember like the last homework assignment had like page 202, number 23 and 24? You try those tonight. Those are the imaginary ones, just like this. Okay. Descartes' rule of signs really isn't, I mean, like once you kind of get going on it, isn't too bad. I would recommend for the Descartes' rule of signs maybe using like a table. If you look in the back at one of them, they do kind of like I did, like a positive, a negative, and imaginary, and you kind of fill in what the possibilities are. You have to think about all the combinations of what's allowed, okay, within the number of real zeros that you have. Tomorrow we're going to wrap up chapter 4. We're going to take this Descartes' rule of signs, we're going to put it to use with our rational root theorem, so it's all review tomorrow, like putting everything together. And then we'll be reviewing on Wednesday, quizzing on Thursday. I think we review on Friday and Monday. And I believe your chapter 4 test may be a 2-day test. If you check your gold sheet. And that's mainly because, like with polynomials, if you're doing synthetic guess and check, sometimes you get stuck. You need a little extra time.